Hello. Uh, Hello. Can someone in the chat tell? Okay. Yeah. Sorry about that. Okay. Uh, Sorry. I'm extremely sorry about that. Yeah. So from welcome to the post-contest discussion for contest 449, where we'll be up solving this weekly Leetcode contest. So, okay, let's go to the first problem. The first problem is minimum deletions for at most k distinct characters. Okay. So here we are given a string s, which has lowercase English letters, and we are given an integer k. And our task is to delete some characters such that the distinct characters in the string is at most k. Okay. So what does this mean? Let us take an example. So if we are given a string like ABC, then and we're given k equals 2. So that means that distinct characters, so A is a distinct character, B is a distinct character, and C is a distinct character. So we can see that there are 3 distinct characters here. But what we want is 2 distinct characters. So either we have to delete one character, or maybe some character in between, or the third character. So let us take another example. For example, our string was uh, A, 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 B, 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 C, D. So let's say our string was A, 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 B, 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 C, and D. So then what we need to do is uh, we need to delete, let's say we are given again k equals 2. So then here also we need to delete some characters to make sure that number of distinct characters are 2. So here we can see that there are 4 distinct characters, A, B, C, and D. So in this we need to choose 2 of them to delete. So either we can remove, let's say we removed all the A's and we removed all the B's. Then we are left with C and D. Otherwise we could remove C and B, and then we'd be left with only A's and D's, which would also make this equation, which would satisfy the conditions. However, the question asks us the minimum number of deletions required. So how do we approach this problem? The idea is that if we want to find a minimum number of deletions, how many we will first count the frequency of every character. So if you see there are 3 A's, 2 B's, sorry, 3 A's, 3 B's, 1 C, and 1 D. So the idea is first we count the frequency of every character which occurs in this, and then what we can do is we can remove the ones with the least frequency until our condition is satisfied. So how do we do? Count frequency. We can write it count frequency and the second is remove smallest frequencies until our condition is satisfied. I think this is a very natural approach. So like anyone doing this problem would have thought of this, even if maybe if you're new, you might not be able to implement it. But let us try on all the given test cases and see if this works. So for example, we have the test case AABB and k equals 2. So AABB and k equals 2. So since k equals 2 here, we can see that there's exactly 2 distinct. There's AA and BB. So in this case, we'll get frequencies 2, 2. But what happens is, since we only need 2, this condition is already satisfied. So our answer is 0. Okay, let's check the other case. The other case is y, 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 z, z, and k is 1. Y, 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 z, z, and k equals to 1. Okay, so for this, we can see that we need at most one distinct character. So we have an option. We can either remove all these three y's or we can remove these two z's. The frequency of y is 3 and the frequency of z is 2. So in this clearly, all we need to do is remove the smaller frequency. So we remove the smaller frequency, which is 2. So then we get our answer as 2. All right. Is this much clear? Can someone tell in the chat? Yeah, we'll discuss the third question, but we'll discuss the second question also because like we'll discuss all of them in order. So we'll discuss the third question after discussing the second one. I hope that's fine. Okay. So let me just explain one way to write the code for this. One way is you can simply have a frequency vector since there are at most 26 characters. So we can have a frequency vector of size 26. Frequency vector of size 26. Size 26. And then we can sort this vector, sort this, and then we can keep only highest k. What does this mean? Let us take an example of, let's say, AA, BB, C, D, E, and k equals 3. K equals 3. So for this, our frequency vector will look something like this. For A corresponds to 0. So A has a frequency of 2, B has a frequency of 2, C has a frequency of 1, D has a frequency of 1, E has a frequency of 1. And then we get all zeros because frequency of everything else is 0 up till 26, up till Z. So then once we sorted this, in this case, it's already sorted, but once we sort this list, we can only keep the first K and remaining everything we need to delete. Okay, let's see what the code for this looks like. So, okay, the first observation which we had was, yeah, removing a character which occurs a lesser number of times is more beneficial. The second observation, so that was pretty much the only observation. So then the solution is find frequency of every character, remove elements with minimum frequency until at most k characters remain. Let's see the code. Okay, so the code for this, we are using the approach which I just explained. We create a frequency vector for all 26 characters. Then we increment the frequency, like we go through each character and we increment the frequency. We sort this frequency vector. And yeah, so if you sort it in reverse, you can keep the first k characters and delete everything else. Otherwise, if you sort it from ascending order, then we need to keep the last k characters. So here we sort in ascending order, and everything up to the last k characters must be deleted. So we add the frequency of those and we simply return. I hope this much was clear. Okay, someone gave a test case UXYHF7. Can you clarify? Krishna Kumar. Yeah, you can also do this with map, or you can use priority queue, or pretty much any data structure. I decided to only use vectors since they're the most basic data structure available. But obviously, if you use a map also, this will be very simple. You must just put all the values in a map and then you can put all the values in the map same way we have done it here, and then choose the largest ones. So you can use a priority queue, or you can just you can put the values of the map back into a vector and sort it. So any of those ways work, yes. Okay. Any doubts on this question, or we'll move on to the next question? Can someone write in the chat if we should move on to the next question? Okay. So moving on, the next question is some grid partition. Uh, in this, we are given a grid of m by n size. We are given a grid of m by n size of positive integers. Our task is to determine if it is possible to make either one horizontal cut or one vertical cut on the grid such that each of the two resulting sections are non-empty and the sum of elements in both sections is equal. And we have to return true if such a partition exists, otherwise return false. Okay, so let us understand what that means. What we mean is, let us take a example grid. Let's say our grid is like let's just take their example. 1, 4, 2, 3. So if this was the grid, then we can see that if we take this horizontal line, the sum over here is 5, and the sum over here is 5. So there's at least one row or column where we can split along to get an equal sum. So it's a very intuitive question. It's basically asking if there exists such a line. So let's take some other example maybe. Let's say we have a grid like this. And we have something like 2, 2, 2, 3, 4, 5, and 2, 2, 2, 4, 6, 2. Then again, we can see that now instead of a horizontal split, there's a vertical split here. We can check the sum. So we can check the sum. The sum here will be 18 because 2 plus 2 plus 2 plus 4 plus 5 plus 3, 18. And then the sum here also will be 18. Like if we check the sum of this row, then it's 2 plus 6 plus 2, 10 plus 18. So here also it's 18. So we can see that either horizontal splitting or vertical splitting, both are counted. And if any time we see that it's equal, we can return true. Otherwise, if none of the splits are possible, we have to return false. So this is the question. Now, okay, Krishna Kumar. For that test case, the answer should be 0, since the number of distinct values is less than 7, because the length of the string itself is less than 7. UXYHF. This is for the previous question. Sorry. Krishna Kumar asked if UX, Y, H, F, and K is 7. For the previous question, for question number 1, the answer to this should be 0 because we don't need to delete anything. Number of distinct values are clearly 5. Number of distinct values are 5 because the length of the string itself is 5, so we don't need to delete anything. Yeah. Okay. So moving back to the second question, um, let's see how to approach this problem. So first, let us call the whole sum of the array whole sum, or maybe the sum of all the values, sum of all values of this matrix. S. So let's call this sum S. Okay, so if the sum of all values is S, now what we can say is anytime we make a division, let's say we make a vertical division. A vertical division just means that we're doing a column-wise division, like the first column is the first vertical division. Then if we move this right, that will be the first 2 columns. And then if we move this one more step to the right, it will be the first 3 columns. So anytime we make any of these vertical divisions, so we have a vertical division, and the sum on this side is x. Sum of this side is x. Then the sum on the other side, it will clearly be s minus x, correct? The sum on the other side will be s minus x. So basically what the question is asking, when we try all these divisions, is there a point where x so this is what we need to check basically. So here x is the partial sum and s is the total sum. And basically we need to find a place where x equal to s minus x. So this is our condition. Now how do we solve this? What we can do is computing partial sum is very easy. What we just need to do is given the grid to compute partial sum, all we need to do is iterate over the grid. Like we can do for I from 0 to n minus 1, and we can find partial sum, let's say partial sum of this. So at I equals 1, this will be the partial sum. I equals 0, this will be the partial sum. And then at each point, I equals 0, here is I equals 1, I equals 2, and so on. So at each point, we compute this partial sum by simply adding. So we get a partial sum x, and at each point we check our condition. So this is the pretty intuitive solution. So let us try this on some test case. Dry run of how this is supposed to look like. Let's take some test case they've given. Let's take a false case, 1, 3, and 2, 4. So we get 1, 3, and 2, 4. So yeah, so if we have 1, 3, and 2, 4. So first let's find column wise and then we'll do row wise. So first we find the sum of this column. Sum of this column is 3. This is our split. Sum of this column is 3. I equals 0 right now, or I equals 1 depending on your viewpoint. Sum of this column is 3, and therefore now we check the total. First we find the total sum. Total sum here is 1 plus 3 plus 2 plus 4, which is 5 plus 5, 10. Total sum is 10. So first we find our partial sum x equals 3, and then we compare to our total sum. Then we compare to the equation. So we see that s minus 3 is 7, s minus x is 7, and we see that these two are not equal. We see that these two are not equal. So therefore, here we could not find a case. Now there is no other vertical cases, so we start checking horizontal cases. In the horizontal case, we have this one case, like this. And for this, what happens? For this, we get a partial sum x equals 4. And the other side from the equation, s minus x is 10 minus 4 is 6. So we see that these two are also not equal. And we have tried all splits. So now we can see that the answer is not possible. So we return false. False. Okay. Similarly, we can maybe do larger dry runs, but I think you have gotten the idea. So let me just go into the code. Okay. Yeah, so from the constraints, we can see that the time complexity should be mn or mn log mn. So we can see this because the constraints for m times n is about 10 to the power 5. So we get this idea. Okay. So the first observation, yeah, if one half of the sum is x, then other half is s minus x, where s is the total sum. Solution is pre-calculate the total sum s. We can calculate the partial sum for the first I columns and check if the condition is satisfied at any point. And then similarly find the partial sum of rows and check the same condition. So what does the code for this look like? Let's see. Okay. So first we find m and n, which are defined to be the height and the width of the grid. Then we initialize sum equals 0. This is our s. And we go through each cell in the grid and we add the value of that cell to the sum. Note that for this, we need to use long data type, since the values of the grid can go up to 10 to the 5, and there are about 10 to the 5 values. So the total value becomes 10 to the 10, and it's best if we use long data type for this. That's why I defined long here. Now we're going to calculate the partial sum. So for I from 0 to m minus 1, why till m minus 1? Because if you look at the diagram, or if you look at the question, we can't have an empty sum over here. So we're only doing till m minus 1 because we can't have an empty sum on this side. That's why only till m minus 1. We find the sum by adding this column. We increase the partial sum. So for all j values from j till n, we add this. Then we check our condition. If partial sum equals sum minus partial sum, if this is true, we return true. Otherwise, we just continue checking. Now again, to check column wise, we set partial sum equals 0. We go through each column, we sum the partial sum, and then we do check the same condition again and return true. If none of these conditions satisfy, we return false. So we can see that the time complexity of this is also n times m, which is perfect for the expected time complexity. And we have successfully solved the problem. Okay, question 3 is wrong. We'll see. Okay, so now let's move on to question 3. Does anyone have any doubts in question 2? Can you put in the chat? Or anyone wants me to explain more or some case which they don't understand. If you can put in the chat whether you want anything. Or should we move on to question 3? Let's give a moment for anyone if they have any doubts. Okay, so moving on to question 3. You are given an undirected graph of n nodes, which are numbered from 0 to n minus 1. Each node is connected to at most 2 other nodes. So this is very crucial. Each node is connected to at most 2 other nodes. The graph consists of m edges represented by an array edges, where edges of I is ai bi. So this is standard, and tells you that there is an edge between 2 nodes ai and bi. Okay. You have to assign a unique value from 1 to n to each node. So as you can see, here's a graph, and they've assigned some values from 1 to n. And you must assign a unique value from 1 to n. The value of an edge will be the product of values assigned to the 2 nodes it connects. So we read this carefully. Value of an edge will be product of values assigned to 2 nodes it connects. So your score is the sum of the values of all edges in the graph. Return the maximum score you can achieve. Let us see the time complexity for this. So n goes to about 10th power 4. So what that means is n log n or n root n also maybe, but n root n is unlikely, but yeah, n log n, n root n both should pass. N square quite will not pass, I think, because 5 times 10 power 4 will be too tight for n square. But n log n or n root n should pass. O of n should also pass. Okay, let's discuss what this problem statement means. So first we're given undirected graph of n nodes, where each node is connected to at most 2 other nodes. Let's make something like that. Uh, let's say this can be connected to at most 2 other nodes. So we have this, let's say like this. And then we have another part of the graph, which is like another component in this graph, which is something like this. Okay. So here n equals 1, 2, 3, 4, 5, 6, 7, 8. Okay. Here n is equal to 8. So the numbers of the nodes themselves don't matter to the question. So I'm not going to write that. What I am going to write is like an assignment. So one way, let's say, to assign will be something like this. 1, 2, 3, 4, 5. Let's say we assign like this. This is just an example. And 6, 7, 8. Okay. So let's say we assign these unique n numbers. We have to assign unique value from 1 to n. So we assign this unique values from 1 to 8 to these nodes. Okay. Now let's see what the value of edges will be. So value of an edge will be product of values assigned to 2 nodes it connects. So between these two, we can see the product of 2 and 1 is 2. And here between these two, we can see the product of 2 and 3, it's 6. Here product of 3 and 4 is 12, 20, and so on. Yeah. So when we sum this, we get some value. So the question is, what is the maximum sum we can achieve if we assign our numbers correctly? Now, right away, this is not a very easy question. Just looking at or hearing about the problem, you won't get an idea. Yeah, okay, Nikhil Soni says, can you please try my test case on your solution? Yes, after we discuss it, I'll try my test case, your test case on my solution. Okay. Now let's pay attention. Okay. So let's break this problem down. First thing the problem says, first observation is that uh, edges is less than or equal to 2 for a given node. What does this condition mean and how can we break this down? Okay. So what does this condition mean? Um, Consider what happens if we have a node. Now, if we have one node and we draw an edge from it, right? We get this. Now we know that each node has this condition that edges are less than or equal to 2. So if we continue drawing edges, we can see that we're forming this sort of chain, right? Because now we can never have a branch. We can never have this. This is not possible. We can only have chains. Or become a tree like that. So it's going to form chains, or the other thing it can do is form a cycle. So either it's going to form a cycle or it's going to form a chain. So these are the only two possible types of component of our graph. And that should be maybe easily guessed by the test cases also, because if you see the test case, the examples they've given, this is a cycle, this is a chain, and this is only a cycle. So we can see that all the components in the graph will be either cycle or chain. So one of two types. Okay. So this is our first observation that we can write it like this. Observation 1, every component of our graph is either a cycle or a chain. Okay. Now, second observation, let us try to solve in a simplified form. Let us try for what if there was only one component in the graph and it was a cycle. So let's say only cycle. So let us solve the simpler version of the problem, only cycle case. There was only one component of the graph and it is a cycle. So what we're doing is basically we're breaking down the problem. We know that since this rule implies only cycles or only chains. So first we'll solve for a graph in which there's only a cycle, and then we'll solve for a graph where there's only a chain. So let's say we have a cycle here. Let there be, let's say, 5 nodes. So there are many ways of assigning values to these 5 nodes. So for example, we can assign 1, 2, 3, 4, 5. But you should get the intuition that this will not be very good. Since see, 5 is neighboring 1 and 3 is neighboring 2. So these large numbers which would have neighbored each other and made the sum larger are neighboring smaller numbers. So here's the intuition behind this. Let's say we have a node 5. Let's say this node, since in a cycle all the nodes are symmetric, so we can say any node we can take and we can put the highest value on it. So we can say, let's say this node has value 5. So we want to maximize the products and the sum of products. So we'll put 5 next to 4, of course. So we'll put 5 next to 4 because we have this intuition that 5 times 4 is 20, and that's the largest possible product we can get. So we'll put a 5 next to the 4. Now next 3. Where should 3 go? Where should 3 go? Okay. So where will the 3 go? The 3 will go next to 5. Why? Because each time we're choosing a number, we're doing a greedy strategy. We're placing it next to the largest number available. So when you're trying to insert the 3, you're going to find the largest number and you're going to insert it next to that. Why is this? Because 3 is the largest remaining number and this is the largest current number. So next to that, we'll place 3. Okay, now which numbers are available? Right now, 4 is available and 3 is available. And the next value we need to put is 2. So now where should 2 go? Obviously, 2 should go to the largest number available, which it can go adjacent to. So 4. So the best thing it can be adjacent to is 4. So we'll put a 2 here. So that 2 and 4 can be neighbors and give a product of 8. Now 1 is remaining. Where should 1 go? 1 should go to the largest number it can be adjacent to, which is 3. So this is the largest number it can be adjacent to. So we put 1 over here. So we get this like alternating pattern, 5, 4, 2, 1, 3. Like we see odd numbers are here, even numbers are here. Something like that kind of pattern we're getting. And you can try it out for yourself by writing many cases that this is the case which gives the maximum value. So a lot of this problem is also a lot of writing cases and seeing what works. But the argument behind this is a greedy strategy. The greedy idea is that let's try for a larger case. Let's try for maybe 8. The idea is that every time we need to put a number, we'll put it next to the largest number which is currently available. So here it's for n equals 8. So 8 itself can go anywhere. Since this whole cycle is symmetric, 8 itself can go anywhere. And then the remaining will fill with greedy. So 7 will go to 8. So it can be here or it can be here. It doesn't matter. It doesn't matter which side 7 goes. So we'll put it here. Or let's just put it here. Okay. So 7 goes here. Now 6 will go next to the largest thing possible. So 6, will it go here or here? So obviously 6 will go next to 8 since that's giving us a maximum sum, maximum product. Then 5 will go here since you can see 5 into 6 and 5 into 7. So it's better for 5 into 7. Then similarly 4 will go here. 3 will go here. 2 will go here. 1 will go here. And we get this interesting alternating pattern. Again, as you can see, all the odds are on one side. All the evens are on one side. That's one way you can see this pattern. Or the other way is just basically the largest numbers are as close to it as possible. That also you can see. Like there are many ways to visualize this or write the pattern. So now we know the pattern for cycle case. Now let us see only chain case. Is this much clear? Like the intuition at least, that why I'm putting the numbers like this? Okay. Now only chain case. Let's say we're given a chain like this. All right. And let us number the values. So obviously there are many ways to fill it, but how exactly do we fill it so that, we get the maximum value? So it is very similar to the cycle case. It is very similar to the cycle case, except we simply don't have this edge. If we had this edge, it would be the exact same as the cycle case. So basically, this is cycle case with one edge removed. You can see that this is the same as cycle case minus one edge. So basically the idea is we're going to solve the cycle case for this, and we're going to remove the edge of minimum weight. So for example, if this was our cycle and we had to make a chain from it, then we would remove this edge and just make the chain. So we remove the minimum weight edge from a cycle case and we get the chain case. So let's write, uh, let's solve first as a cycle case. So as a cycle case, let's say, um, say this was 7, then let's say this was 6, this would be 5, this would be 4, this would be 3, this would be 2, this would be 1. Now we can see that in all the edges, this is 2 into 4, this is 4 into 6, etc., etc. So in all edges, this edge has the minimum weight. This edge has the minimum weight. So basically, the answer will be simply the cycle case minus this edge. Okay, so that is almost all the observations needed to solve this problem. The last and final observation is, or actually second last, cycle case is better than chains. Like if we can make cycles, it will always be better than chains. Why is that? For example, if we have a graph in which there's a cycle also and there's a chain also. So this is the first example itself. If we see the first example itself, this example, is better to start first with the cycle. It's better to do 7, 6, 5, 4, 3, 2, 1, rather than doing this, uh, starting with the chain and then doing the cycle. So what happens if we start with the chain? What happens is, let's say you start with 7 and then you get 6, you get 5, and you get 4, right? Then you get here 3, 2, 1. Now, if you see the difference between these two cases, here we're missing this, which is 4 times 5, but we got a 1 times 2, right? So basically, and here there's a 6 times 5, basically. So the idea is that we the the values of the since the chain is missing this final connection, the chain is missing this final connection. It's better if this final connection has lesser weight. So this final connection, better if this has less weight. So first we should number the cycles and then we should number the chains. So that's basically the idea. First we number the cycles and then we number the chains. And of course, our final idea is very trivial, but I'll still mention it. Because first we number larger chains and then we number smaller chains, because then the missing value will be smaller. Although this is I think you can do it without this also, but yeah, like there might be ways to do it without this. But first we'll number the larger chains, then we'll number the smaller chains similarly for cycles. So let us do a example, and using everything we did just now, we're going to see how to solve it. Okay. So is this, we can discuss D at the very end. Uh, Although I did not solve D during contest time, but I do have an idea about how to solve it. So we can discuss that as a bonus for this session. Okay. So let's say we have a graph which looks like this. So these are all the components of this graph, one big graph. So this is our example graph. Here the value of n is 1, 2, 3, 4, 5, 6, 7, 10, 11. N is 14 here. Okay. So first we need to start numbering cycles, and then we need to start numbering chains. And the reason for this is that when we number cycles, we don't miss this extra edge. So that's why it's better to number cycles. And also better to number larger cycles since we can get more edges out of them. So the first number, we let's say choose any node here and put the number 14. Then and adjacent to 14 we have a 13. Adjacent to 14 we have 12. And adjacent to 13 we have 11. Okay. Then we number the next cycle. So the next cycle will be 10, 9, 8. And then after this, we'll number the largest chain. So the largest chain is here, this chain. So this chain will number. We can number it as 7, 6, 5, 5, 4. Then here simply 3, 2 because there are two values and 1 for the last. So basically, we're going to number first cycles, then we're going to number chains, and we're going to number them from largest to smallest. And we can see that all of this has very strong intuition behind it, since as we saw, all nodes are symmetric. We're greedily numbering. For chains, it's basically a cycle without an edge. So we're first making the cycle and removing the smallest edge. We can see why cycles are better than chains, and we can see why larger cycles are better and larger chains are better. So how do we code this? Code. So let's discuss the code for this. Um, the first step is to do a DFS and find components. And find components. So we don't actually need the components themselves. We just need sizes of all the cycles and sizes of all the chains. We can store this in a vector of one vector for cycles and one vector for chains. We can sort that vector to have them from largest to smallest. Then we can number them according to this pattern. numbering according to a pattern is like a very much pattern question. So for a cycle, we can start at any point and we can choose. And we don't actually need to number. We just need to find because the question asks just for the final answer. So we don't even need to number the nodes. We just need to find the final answer. So we can calculate that. Calculate the answer. Okay. So let us see what this looks like in a dry run. Dry run. Okay. Let's say I take some nodes. I'll make a new example right now. Not too big because otherwise it'll become a bit long. But yeah. And let's say this is our example. So first, what we're going to do is we're going to DFS through our nodes. So let's give these nodes some numbers. Let's say this is node 0, this is node 3, this is node 1, this is node 4, 2. These are not values. These are not values. These are just index of the node as it is given to us in the question. So 5 and 6, 7. Okay, all right. So what we're going to do is we're going to visit each node one by one. We're going to do a DFS basically. If it's unvisited, we will do DFS on this component. We'll mark all of them as visited. We do not detect cycle. Mark as visited. Size is 3. A DFS can easily find the size of the component. Mark as chain. So since we did not find a cycle, we know that we can use DFS to find a cycle. If there was no cycle, it must be chain. So we mark it as a chain of size 3. So our chains currently looks like this. Because we have one chain of size 3, and cycle looks like empty for now. Okay, so now we visited node 0. We try visiting node 1, but we see that that's already visited. Then we try visiting node 2, and we see that that's unvisited. So from here, again, we do a DFS. And when we do a DFS, again, we can mark everything as visited. We can find that the size of this is 8. Sorry, the size of this is 5. Size is 5. And because we detected a cycle, we know that we can detect cycle with DFS. We just need to check if the if the node is not a parent and it's already visited, then we know that there's a cycle. So we can see that there's a cycle here. So since our DFS said it was a cycle, we can add this to the cycle, and we can say that there's a cycle of size 5. Is this clear? Yeah. Okay. So then after this, now we have identified all the cycle and all the chain in our graph using DFS. Let us see the code for this also. So what is the code for this? So we have long max code. This is the defined, this is the question, uh, the predefined function. So what we're going to do is we first make an adjacency list from the edges. So taking the edges, we make an adjacency list. Then we make a visited array, which is true or false, depending on whether a DFS visits or not. We have a vector called cycles and a vector called chains. And every time we we find a cycle, we'll push its size into cycles. If we find a chain, we'll put its size into chains. Now, for each node from 1 to n, if it is visited, we don't do anything. We just continue. Now we set count equals 0. Count is number of nodes which we are going to have in the component. Then we do a DFS. Okay, let us see how I define this DFS. This DFS, it returns true or false. It returns true if a cycle was found and false if a cycle was not found. And it keeps tracks of count, which is the number of nodes visited. So it takes adjacency list, visited array, count, I is the node, P is the parent. Okay. It increments the count for each node. It marks the node as visited, and it says that answer means cycle. Cycle. Okay. So now for all adjacent nodes, if the adjacent node is equal to the parent, then I don't need to do anything. But otherwise, if the adjacent node was already visited, then there is a cycle. I know this because in DFS, if you have to find cycle, adjacent node visited means cycle exists. Right. Skip parent node. All right. If the adjacent node was not visited, then visit adjacent node. All right. So that's basically the way. And we're doing or equal to means if there's a cycle detected in this part, then that means there's a cycle detected in the whole thing. So that's why we're doing or, so that we finally return answer, which means whether there's a cycle or not. So basically, if we find a cycle, we push the size into cycles. Otherwise, we push the size into chains. Is this part of the code clear? Anyone? If it's confusing, I can try and explain again. You can write in the chat if it's confusing. Okay, now I'm going to the next part of the code, which deals with actually finding the maximum product, maximum sum of products. Fine. So now that we have found all cycles and chains, we can go to the second part. So first we sort all cycles and chains so that we have the largest cycles first. Sort in descending order. So this is to make sure that we have the largest cycles first. As you can see, we sort from R begin to R end, which means that it's going to sort in reverse order or in descending order. And then finally, we need to calculate the values of the product. Okay. So let's say we have a cycle of size n. So cycle of size 5. What is the product we can get? And our n currently is something. And n is currently k. What I mean by currently k is n might, like when we use up numbers, the the values get smaller. So the largest unused number till now is k. And we're currently trying to process this cycle. So basically what happens is we get k here, k minus 1 and k minus 2. We have seen this earlier. Here we get k minus 3, k minus 4. So basically this is like, since a cycle is always size 3 or more. So basically this is like k minus 1. So something we have by default is k minus 1 plus k minus 2. Right? So this we always have in any cycle, that k minus 1, k minus 2 we always have in our product. Now to increase this product, we have each number till n reaches. So let the size be x or something. So let the size be x equal to 5. So till n reaches k minus x, till n reaches k minus x, what we need to do is we need to see k minus 3 is getting paired with k minus 1. K minus 4 is getting paired with k minus 2. So what basically we need to do is we need to do n times n plus 2. Basically, every time we are at some n, we have to multiply it with n plus 2 so that we can get the correct product. And then we decrement n minus minus. Here we are doing n minus equal to 2 since 3 nodes are colored. So basically, we're going to decrement n as nodes are getting colored. Yeah. It'll be clearer in the code. So we first set our answer equals 0. And then for each cycle x, whatever the current value of n is, I'm going to add n times n minus 1 plus n minus 2. This is basically the k minus 1 plus k minus 2 case. I add that. N decreases by 3, x decreases by 3. Why is this? This is because 3 nodes have been colored, have been given numbers, basically have been given values. So I can decrease my value of n. And similarly, I can decrease value of x because 3 nodes have been 3 nodes in this cycle have been covered. Now, while x is greater than 0, what I'm going to do is I'm going to multiply answer with n plus 2. So basically, this is what I'm doing. This is n. Currently, n is k minus 3, and this is n plus 2, which is k minus 1. So each time, we can see that we are multiplying with n plus 2. And then finally, our answer gets. Now, finally, when all of that is done, we have this final edge. The final edge, which I'm drawing in blue. This final edge is left. And this will simply be uh, n plus 1 times n plus 2. So once n has decremented, n will have decremented to n minus k. Sorry, n will have decremented to n minus x. So at this point, n plus 1, n plus 2 means that this is k minus 3 times k minus 4. So that's what is in the code here. Now for chains, it's the exact same idea, except we don't do the step. We don't do this final step in blue. For chains, is the same idea. Same idea without final step. Final edge basically. And for a special case for n equals 1, for x equals 1 and x equals 2. X is size of the chain. So special case is this. If we have something like this, or we have something like this. So these two cases are special case. And one sec. I think there was a slight issue with the board anyways. Okay. So special case is so in this cases, we can see that the value will be here, there'll be no value of the edge, so 0 will get added. And here, whatever n is, n times n minus 1 will get added to our answer. Okay. Right. So it's the exact same code for cycles as in chains, except here n times n minus 1, except here in the end, there won't be this addition because the final edge is not there. And similarly, there'll be a special case for x equals 1 and x equals 2. where 1 and 2 are the size of the chain. Okay. So yeah, that's about it. First, what all did we do? First we found all cycles and chains. Then with DFS, and then second we sorted them, and three we numbered them in this procedure. Okay, so we have some questions. Madhu says, can you explain n times n plus 2? Okay, so let me draw the case again. I don't know, unfortunately, the board was erased a bit. 1 second. Oh, okay. Right, it's still here. Sorry about that. Anyways, so let's say here's a cycle. Then I'm explaining why n times n plus 1. So in the start, let's say n is 7. Our cycle size is 5. So the numbers which will come on the cycle will be 7, 6, 5, 4, and 3. Right? Just think about it. If n is 7 and x is 5, then these will be the numbers on the cycle. Correct? According to the method which we discussed, these will be the numbers on the cycle. So now in the start, n is 7. So we'll add uh, in the start n is 7. So we add n times n minus 1 plus n minus 2 to our answer. So this will cover this. N times n minus 1, n times n minus 2. Okay. Now that we have covered these three nodes, I'm going to decrement n with 3. So now our n has become 7 minus 3, or n has become 4. If you look at the code, first we add this part, then we decrement n with 3, and now my n has become 4. Now till some nodes remain, till x is greater than 0, I do the following. I add n times n plus 2. So what does this mean? I add 4 times 6. So right now n is 4 and n plus 2 is 6. So I add this. Here in this example, it will be 4 times 6. This will be how much in this example? In this example, this will be 7. So this will be 4 times 6. Right? And then again, I decrease n. N minus minus. So now n is 3. So that means I'm now here. And now again we multiply n times n plus 2 because that's how we saw our pattern was like this, that we were pairing n and the n plus 2th value. So we get n plus 2. It will be 3 times 5. So we get a final answer. And now once all of this is done for the cycle case, we need to multiply n plus 1 times n plus 2. Why is this? Because once everything is done, we have these two remaining, like this final edge. Why is that? Because now, after everything is done, our n has become 2. Like, because we did n minus minus here. Now n is 2. Now at this stage, we're adding n plus 2 times n plus 1. Because n is 2, that means we're adding 3 times 5. So we add 3 times 5 finally. So as you can see, final answer, it is this. 7 times 6 plus 7 times 5. 7 times 6 plus 7 times 5. Here and here. 4 times 6 plus 3 times 5. 3 times 5 plus, this should be 4 times 3, sorry. 4 times 3. Yeah, so plus 4 times 3. So is that clear? Yeah, okay. Uh, right. Okay, now I can do Nikhil. Sony, can you give me your test case? You said that I can try a test case. Okay. Yeah, yeah. Raghav, I'll address your issue. Okay. So for chains also, it's the exact same logic, except we don't do this part. We don't do this for chains because the last edge, it won't be there in chains. So final edge of cycle. This will not be there in the chain case. So that's not going to be there. And for chain, there's a special case if x equals 1, if x equals 2. If x equals 1, at that point, you can just break size to chain. So in a size to chain, they're just two values. So we just do n times n minus 1. We make n minus equal to 2 and we continue. Otherwise, we do the same process which we did for cycles. As you can see, this are exact same process. And then we finally return the answer. So that's all. You can see that we have successfully solved this question. The code for this, as well as writing for this, we will share after the session. Okay. Okay, Nikhil, your case is pretty long. So, like, I guess if we try to do it right now, it might take a bit of while. So, I guess you can always, uh, if you leave a comment on the YouTube video for this, then I'll reply to it after the session. Or otherwise, you can always make a doubt in our doubt solving, and I'll reply to it. All right. So, question 4. So, we'll discuss a little bit of question 4. Um, although this stream is not meant for question 4, we'll still discuss it a little bit. Um, so yeah, in question 4, it's the same question, equal sum grid partition, except the additional part of this is that. By the way, the whiteboard, the code, and everything will be shared. I'll write it more neatly and I'll share everything to you. The whiteboard, the code, and also this document which explains each solution and has code for it. So we'll share it maybe half an hour or 20 minutes after the session is over. Okay. So the question is the same as the grid question. The fourth question is the same as the grid question, except here to make the left and right side equal, we can remove any cell. We can remove any one cell in either this side or in this side. But the idea is, it says that question one. Wait, why is it on? Yeah. We can discount at most one single cell, and the rest of the section must remain connected. So it must be non-empty, must discount at most a single cell, and the rest of the section must remain connected. So in this, basically what we need to do is we need to keep a multiset of or some other data structure which keeps track of what values were there in these cells. I'm going to give a very quick explanation for this, since this session wasn't meant to explain D as well, but I'll just give you the idea that when we move from left to right, we keep track of which elements are there in our partition. So let's say the elements were there like 5, 4, 3, 2, 1, 6, 2, 5, 4, 2, 1, 0. So the same idea as before. We have our value S, and here we have X, and we want to make X equal to S minus X, right? We want S equal to X minus X. But if S is not equal to S minus X, if we can remove one element such that the remaining elements remain connected, these remaining elements remain connected, and then the sum becomes equal, then also it's valid. So the idea is that, let's say if we yeah, you can use map also for question 4. Anyways, so question 4, actually we're not going to explain in much depth. I'll reply to comments on YouTube if you want. So basically what we're going to do is, you can remove an element and you can store it in a, so basically when you run the partition from left to right, you can store the elements in a multiset or a map. In map. So it's the same as question 2, but we're storing the elements in a map. If this condition is not satisfied, then we find the difference between S minus X. If this condition is not satisfied, we find the difference between S minus X and X, right? So now this difference we have to see if this value is there in a map, in this map, or we have another map for the other side. So if this value is there in this map, and we can check if removing one value satisfies this condition or not. Now, there's a tricky part of this question, is that when there's only when the vertical line is right here, let's say at I equals or j equals 0, if the vertical line is right here, then we cannot remove some cells. That's because it'll make this part disconnected. So for example, if this was let's say 5, 4, 3, and if we can remove somehow this 4, the 4 in here, if we had to remove 4 and make them equal, we cannot remove 4 because otherwise 5 and 3 will become disconnected, right? So whenever j equals 0 or j equals this thing, n minus 1, or otherwise, there's only one row or one column on the other side, then it's a special case, right? And we can't remove something from the middle. So I guess uh, someone who asked this, someone who said 981 out of 982 test cases, right? Who was it? Raghav. Yeah. So if you do only this much, you will get exactly 981 out of 982 test cases. But the final observation is, if this was if your elements are exactly like this, if this is your matrix, it's just a straight line. That means number of rows is 1. This is a final special case. For the fourth question, we have a final special case, which is, I think, the most trickiest case, is that if your whole matrix is a line itself, then we cannot remove any value from the middle like this. Like, see, if let's say this is our vertical line, then if we remove some value, let's say we remove this 7, and we could make the x and s minus x values same by removing this 7, but we can't remove this 7 because then this part and this part become disconnected. So this only happens when your matrix is like this degenerate matrix, or it becomes like a array or a horizontal line. So if your matrix was something like this also, if your grid was something like this also, then you have some horizontal line like this. We cannot remove some value in the middle because then it will become disconnected. So I think this is the last test case you are missing for Raghav. Okay. Any other questions? Nikhil Soni, I'll run your code. Okay. Uh, After it, I can I can show you that my code does pass all test cases and the greedy solution works. Anyways, so what else? What is the expected rated if this was a CF problem? Okay. So I guess for CF rating, um, question 1 will be like 800. Question 2 will be maybe 1100. Question 3 should be, I think, 1600 or 1700. And question 4 also will be, question 4, the implementation becomes very long. That is why it is hard. Otherwise, the idea is easy. So question 4 will also be 1600, 1700, or maybe 1800 also. I'm not sure, depending on implement. Because I also got stuck during the contest. I could not solve question 4, even though I had the idea because of implementation issue. So legendary clashing, uh, I will send you a reply on YouTube for this. I don't want to run the test case right now because like even my implementation was buggy. Okay. Leetcode does not include this test case. Fine, I will implement it and I will either reply to you on YouTube, or I will, if you make a doubt on the TLE doubt solving platform, I'll run the test case and I'll show it to you. We'll release the codes for this session afterwards, and we'll give you the document. We'll give you this drawing board. So I hope this cleared some doubts. Okay. So anything else by anyone? Because question 4 I'm not running because actually I did not solve it in the contest. I also got I missed this last case. This last case I also missed. So uh, this I realized after the contest. So that's why I'm telling you. But I will implement this and I'll send you the code. All right. Okay, then thank you everyone. Thank you for attending this session and I hope you learned something. Please subscribe to TL Eliminators and see you in the next PCD.